Prim's algorithm is but one of many, many, many minimum spanning tree algorithms out there. So let's talk about another one called Kruskals algorithm. So Kruskals algorithm has the neat property that in efficient implementation is relatively easy to do, unlike Prim's algorithm. Like getting an efficient Prim's algorithm is a little tricky, but Kruskals algorithm is really intuitive to understand and really intuitive to implement. So it's kind of nice for that reason. Okay, so what we're going to do here is we are going to assume that we have all of our edges somehow in sorted order, and we're just going to step through them one by one, and we're going to add each edge as long as it does not cause a cycle. Now it turns out that this is really just going to be using the cut property in disguise, but let's just naively proceed with the algorithm and see what happens. So we start by looking at the smallest weight edge and we say, if we add this to the minimum spanning tree, does the minimum spanning tree have a cycle? Well, clearly not, right? It's just a line. All right, how about if we add this next smallest edge to our minimum spanning tree? Will this cause a cycle? And the answer is no, right? So we add that to our spanning tree. Next up comes 3, 6. Will that cause us to run into any kind of trouble as far as cycles are concerned? No. We add that, and it's fine. Now here's a funny feature of our spanning tree that we're building. It's not fully connected at all times. Unlike Prim's algorithm, which has the invariant that the minimum spanning tree under construction is always connected, that is not the case with Kruskals. Nonetheless, once you're done, it will be all connected. So this is fine, the fact that it's doing this right now. All right, how about 5, 6? This is our next edge in the list because it's the only one with weight 1 left. So in this case, this edge does not cause a cycle. Okay, next comes 0, 1. This does not cause a cycle. All right, next up is 4, 1. Does this cause a cycle? Yeah, causes a cycle. So don't use that one. That's not good. And then how about 4, 3? Does that cause a cycle? No, does not cause a cycle, so we'll include it in our minimum spanning tree. And at this point, we have b-1 edges, and so we're totally done. Now, why does this work? Why is this the cut property? Well, basically, whenever we're considering the smallest edge in the graph, the way that the cut that Kruskals' algorithm is thinking about is, let's consider, actually here as an example, let's think about this edge that goes from 0 to 1. So Kruskals' algorithm, what it's doing is saying, okay, one side of the cut is everything that is connected along the minimum spanning tree to one of the vertices on the edges. Oh, sorry, one of the vertices on the edge under consideration. And the other side of the cut is everything else, okay? So in other words, I pick, let's say, vertex 0 arbitrarily between the two vertices and the edge. I find everything that's reachable along the minimum spanning tree, and then I am considering all edges that are separating this cut, okay? Now you'll note I'm not highlighting all of these lines in purple because the way that Kruskals' algorithm is working is it's only thinking about the smallest one. So it's kind of a little clever trick here that we are guaranteed that we're looking at some cut that is useful, all right? So it's a little different than Prim's, where the cut under consideration was very clear. Here it's a little more subtle. So just to point out, if you wanted to prove that Kruskals' algorithm works, this is why it works, because effectively it's picking a cut which is everything reachable along the minimum spanning tree from one of the vertices on the edge. Now you don't have to understand that to know how to run Kruskals' algorithm, but if you want a solid A-level understanding of the topic, it's a good thing to make sure that you understand that proof, or what I mean by the cut that Kruskals is thinking about. All right. Here's a more realistic version of Kruskals. So we saw the conceptual picture of Kruskals' algorithm. And so this more realistic picture, how it's going to work is we are going to use data structures like we did in the more realistic Prims. In this case, we're going to use a priority queue to track all of the edges. We're going to insert them all ordered by weight. And we're also going to have a weighted quick union object that we're going to use to keep track of cycles. Because remember, at the very beginning of this particular set of lectures, we talked about cycle detection. Okay, I don't want, is that the one I don't want? Yeah, there we go, let's get rid of that. So what we want to do is use our priority queue and our weighted quick union object, and then the MST in this case is going to be a list of edges, and we want to use all of these data structures to concretely implement our Kruskals algorithm. So we start by deleting the top element from the fringe, that's edge 0, 2, and then we check to see if there's a cycle, and the way we do that is not through iterating over the whole graph or running DFS, but instead calling is connected on our weighted quick union object. So at this point, no union calls have been made, so everybody is disconnected, and so the answer will be no. So we'll union 0 and 2, and we'll also add the edge to the minimum spanning tree. All right, next edge to come off is 2, 4. So are they connected? Well, we check in the weighted quick union object and we say that 0 and 2 are connected, but nothing else is. So the answer will be no. So we'll union 2 and 4 and we'll add e. And so now we have one big old connected component that's 0, 2, 4. All right, next edge up is 3, 6. So we remove that edge and we check, is it connected? 3 and 6, that is. The weighted quick union object says no. So we'll union 3 and 6 and we'll add e to our minimum spanning tree. So now we have 3 edges in our minimum spanning tree and we have 2 connected components in our weighted quick union that track who's connected to who. All right, next up comes edge 5, 6. We say, are those connected? No. So we'll union them and then we'll add e. All right, next up comes 0, 1. Are these connected? No. Okay, so we'll union 0 and 1 and we'll add e to the minimum spanning tree. Next up, we say, are 1 and 4 connected? Now in this case, our weighted quick union object will return true because 0 and 1 are 1 and 4 are part of the same connected component, and so we will do nothing, right? That means this is not a useful edge. Finally, we get to edge 3, 4. We say, are they connected? Okay, well, the answer is no, so we'll union them, and then we'll add that edge to the minimum spanning tree. And at this point, our weighted quick union object has everybody connected, and we also have v-1 edges, so we are totally done. So that's the idea conceptually. And so why does this work? Again, go look again at this conceptual or realistic demo. This is it written out in text, but it's basically what I described. That for every time you're considering the smallest weight edge, there's some cut for which the cut property proves that the addition of that edge will actually be valid in terms of bringing it into the minimum spanning tree.